it's a pleasure for us to introduce our next invited speaker, Carlos González-Ballestero, that is going to talk about quantum magnonics and applications in quantum information science. For me, that I studied in the Universidad Autónoma de Madrid, it's a pleasure to introduce a mate, because Carlos studied there and did his master's and PhD there with FJ and Esteban Moreno, which both were my professors there. And in 2017, he defended his PhD thesis regarding the action of quantum emitters and nanophotonic platforms. And now, since then, he's in the University of Innsbruck, working in several topics regarding quantum magnonics. And well, the group does a lot of interesting stuff relating the macroscopic quantum superpositions. And I encourage you, if you don't know about the group, to check them out. And without further blah blah, Carlos, the stage is yours.
Okay, thank you. Well, first of all, thank you for having me. It's really great to, as I told you before the talk, I think this is a great initiative, so I'm really happy to be here. So also before I start, I don't know what is your normal format, but feel free to interrupt me if you have any questions. That's totally okay. Okay, so I prefer that. I prefer to cover half of the talk if you understand everything and satisfy your curiosity, than finish it. Okay, so going to the title of my talk, what I'm going to talk about today is it's about, as was said, about quantum magnonics, and in particular, just to tell you in one sentence what this talk is about, so that you can relax. This talk is about trying to introduce for you some excitations that are called spin waves or magnons, and to try to convince you why we and some other people think that they would be really good assets in quantum technology. And finally, to explain to you our research on trying to prove that this is the case. Okay, so this is not still yet decided. Okay, so so let me start by kind of like a bit of a controversial statement, which I call limitations of microwave quantum technology. Okay, and so let me explain what I mean. So by microwave quantum technology, microwave quantum platforms, I'm going to talk about this. I am referring to any kind of quantum platform that is based on microwave transmission lines and or superconducting resonators or qubits, okay, such as, for instance, an example of a kind of like a commercial device. And so, as we all know, I guess in this community, these devices are great. Okay, I'm not going to argue otherwise. These are great and function very well for quantum technology. In particular, two of the really cool things that they have, especially if you compare them with any other solid state excitations or information carriers, that microwaves are really not lossy as compared with other excitations. So they can really propagate for a long time and holding the quantum coherence. And they're also extremely linear, okay, which is very good news, because it also means the combination of low loss and large linearity means that you can encode information in a propagating microwave and just, it will stay there and it will propagate very far without losing its quantum state. However, I mean, if you wanted to dream, okay, there still would be some things that we could try to make better for spin waves, for microwave devices. In particular, they are not, as compared to other platforms, that dynamically tunable. And by this, I mean, you can design these kind of devices, which are, some array of qubits and other elements. And once you design them, then they fulfill a function very well, but it's very difficult to have external buttons and knobs to tune so that you can completely change the behavior of this circuit. And of course, this limits the multifunctionality of devices. Also, and precisely because they are very linear, as we all know, it is quite difficult, again, as compared with other excitations, to exert nonlinear operations, which are the key for quantum information processing, among others. That's why we try to couple photons to qubits, but in general, it's a very big problem of photonics, and not only microwave, but also optical, it's to generate nonlinear operations. And also something that is quite some limitation for microwaves is that they have a very long wavelength, okay? And because you cannot make a device much more than the wavelength in general without having a lot of absorption, this limits the size of the devices. And if you look here, you can see that this device, the scale is about 10 millimeters. So if you want to make your device much smaller, of course, thinking of scalability, this is not easy microwaves. And that's actually, by the way, the reason why a lot of people is still working on photonic platforms with optical photons, because they have smaller wavelengths. And so, of course, all of these limitations and some others are why people is thinking since a long time on devising hybrid quantum platforms. Okay, most of us are already working in this kind of hybrid systems where you basically aim at taking some other system that can complement, that has complementary properties and can complement microwaves, and hope to integrate them in such a way that the combination is better than the sum of its parts. So what I come here to defend is that a very good system to complement microwave devices are spin waves. And so I'm going to get into the physics of spin waves in a second, but just to tell you what they are in a nutshell, they're basically magnetization waves. Okay, these are classical objects. They can also, in some regimes, in some cases, be brought to the quantum regime, and they live in magnetically ordered material. So the idea is you have a ferromagnet, you apply some magnetic field so that all the spins of the material point along the static field, and then you have a fully magnetized material. And on top of this completely ordered structure, you can have some perturbation in which basically the magnetization fluctuates, processes individually across around the direction of static magnetization, and this fluctuation can propagate, and this is what is called spin wave. Okay, so again, I'm getting a bit more into the physics in a second, although the physics is really complicated, and I wouldn't have, not complicated, it's actually simple to describe, kind of, but it's complex, okay, there's a lot of properties. So if you're interested, we can talk more at the end of the talk. But the reason why I like, and many people like spin waves for hybrid technologies is because, first of all, they are very, very tunable, and I'm going to show you an example later. But in principle, by playing, for instance, with the static magnetic field, you can completely modify the dispersion relation and how they propagate. They couple to almost every other external degree of freedom, so they are great for hybrid platforms. They are extremely nonlinear, and this comes from the fact that this has a spin excitation, so spins are very, very nonlinear, and they have a very short wavelength. And this is actually something that sometimes we don't expect, because we are very used to the relation between wavelength and frequency, but this relation, which is given by the speed of light, is not true for condensed matter excitations. In particular, you can have a spin wave with the same frequency as these microwaves and a wavelength below 1 micron. Okay, this can, and this is typical of spin waves or magnons. One of the drawbacks that I want to advertise right away is that they are very lossy. Okay, these excitations, as has to be for any condensed matter excitations, very lossy, but still it is the hope of the community that when we integrate these two platforms together, we can compensate this high loss with the low loss of microwaves, and in principle get better than the sum of its parts. Okay, and I want to highlight extra property of spin waves that I haven't talked about yet, and that's really often overlooked, and this is that spin waves are really technologically advanced. Okay, and this, I mean that there are already many nanoscale devices, many nanoscale magnetic devices that have been developed. Okay, and this comes from the interest from the community that investigates spin waves. That is the magnonics community, which so far is mostly a community dealing with classical physics. And the motivation of this community is to use the spin waves as information carriers in classical computing. Okay, classic next generation computers, not based in electronic currents, but based on other excitations that are less lossy. Spin waves are very good candidates, and I just put here an example where you can see this roadmap that we published this year. But there are many roadmaps, many reviews detailing the advantage of spin waves for classical information processing. And so because of this, there's a lot of nanoscale technology developed. For instance, I just put here an example from our collaborators. One can really engineer nanometric waveguides, which you can image, or where you can check propagation of spin waves. And so because of this is one of the things that makes spin waves really, in my opinion, a bit better than other competitors, is the fact that that not only they have great properties, but they are also very nanoscale, very technologically developed. Okay, so in principle, if one manages to bring these devices to the quantum regime, they should not be that difficult to integrate with current technology. And so, in a nutshell, this is the message that motivates me and other researchers: the quantum magnonic nanodevices. That means taking these devices and bringing them to the quantum regime could be ideal complements to microwave platforms. However, we have a problem, and this problem is that no experiment so far has managed to demonstrate univocally quantum behavior of a spin wave propagating in a nanostructure. Okay, I put here this reference because this is like so far the only quantum experiment with magnons, but this was done in this by the Nakamura group in Japan. This was done with a millimeter-sized single-mode resonator, which is very different from the nanostructures we are interested in, and in particular, this leaves the question open, which is a very hot question in the magnonics community, whether it is even possible to bring nanoscale propagating magnons to the quantum regime. Is the coherence too high? Can we detect them with enough resolution and so on? And so this is a problematic question to answer. Specifically, the magnonics community are a bit at a loss right now because they don't have the tools to answer this question. Okay, in particular, they don't have the theoretical tools to answer this question because developing a theory to answer this question requires to combine two disciplines that are quite complex on their own. One is classical magnonics. I don't have the time to get into the details, but even classical spin waves are really difficult to describe theoretically. Usually, you cannot go in almost any nanostructure, you cannot describe them without heavy numerical simulations. And the reason is they have a lot of complexity, microscopic complexity that has to be taken into account. But at the same time, you have to bring into the quantum regime and moreover in materials. Okay? So you now have to develop a quantum electrodynamics theory in materials that can be lossy, in materials that can be heavily nanostructured, and with a continuum of modes, which in general, I mean, it's doable, but it brings more complication with respect to having just a cavity. So this is the problem that we are facing right now. And so the solution we came about, actually, I was lucky enough to work in nanophotonics in my thesis, and therefore immediately came to my mind that we can basically use the approach of nanophotonics. And nanophotonics, again, is the discipline that's very similar to what we want to do. It's the discipline that studies the propagation of light in nanostructures and has already successfully bridged the gap between two disciplines that are very, very close to this one. So in particular, classical electrodynamics in nanostructures and cavity quantum optics, if you want. And so I'm not going to get into the nanophotonics analogy because it can be get a bit off track. But what this means is we want to use techniques from many systems, from many disciplines. In particular, we want to combine techniques from quantum systems, from condensed matter, usually heavy simulations, to be able to combine these two degrees of complexity. And I'm going to show you some examples now. But what is more important is not really that we want to combine these fields, but that nanophotonics gives us a roadmap, okay? Gives us a plan, okay? What has nanophotonics done in step 1, 2, 3 to unite these two communities? We can look back and see it, and we can try to reproduce this with magnons, okay? And this set us for us the plan, okay? So this is the plan of my research that I am following, and that is not complete, and that I believe will bring us to the quantum regime of magnonic nanostructures, okay? So the first thing we want to do is still in the classical regime, okay? We want to be able to control spin waves coherently, and this sounds, and to generate coherent pulses. And this sounds very stupid because it's very easy to do in nanophotonic structures, but so far the magnonics community, they just have not been able to do it, okay? There was no way to just choose a particular shape of a pulse and generate this pulse in a waveguide, for instance. This I'm not going to get into details, but this point has already been developed. In particular, we have this recent archive where we find a protocol which requires relatively light numerical simulation that allows us to generate pulses with every shape, in particular Gaussian pulses, square pulses, and so on. And the reason why we need to generate these pulses is because they allow us to, so by controlling the classical coherence, they allow us to exploit the wave nature of spin waves. Okay, so far what people is doing, or what people have been doing so far, is mostly just, drive strongly, generate just a lot of magnons or a spin wave in a very incoherent state, and you encode, if you want, you encode information in whether there is a spin wave or there is no spin wave. So there's basically amplitude encoded information. However, one of the big advantages of spin waves, as many people say, is that they are waves, so you can encode information and you can use protocols based on waves, on their polarization, on their phase, etc. And this so far has been quite unexplored. And so this is the first step towards quantum coherent control. This is again the next step. So we want to be able to, once we were able to generate coherent spin wave pulses, for instance, a plane wave, a coherent state, or a pulse with a particular shape, we want to be able to coherently control how it propagates. Okay, so far again, you just generate spin waves and they propagate across the structure. They just move. However, a very core aspect of nanophotonics is the ability to just control this propagation from just being able to devise a mirror so that these spin waves are reflected, to devising a beam splitter, to even more complex structures like a magnonic crystal. Okay, this is the next step. Second step, now getting into quantumness, is of course we need to be able to refine the detection methods. Okay, current detection methods are again relatively low resolution, so they will never be able to detect, for instance, the fluctuations generated by a single magnon. Okay, so if you generate a single magnon state, but you cannot detect it, we are still having the same problem. So we have to theoretically model and find ways of detecting magnons at the quantum level. Fourth point, again, is we need to be able to generate quantum features. In particular, this is universally accepted that what we have to do is to couple magnonic nanostructures to qubits, in particular, probably superconducting qubits, to be able to generate some quantum states, such as single magnons or other states. And finally, we want to propose quantum experiments. Okay, I think it's the duty of us as theorists that if we develop this, it's not enough to just develop this and release it. We have to, go a bit out of our way to propose experiments that the experimentalists can do in the short term. Okay, so this is my map, and so now I'm going to tell you a bit of how we are trying to follow these points, just some of them, because of course this is just an ongoing plan. So I'm going to tell you a bit of how to describe the spin waves in simple nanostructures, so you get a gist of what is the theoretical description of these excitations and why they are so flexible. Then I'm going to focus on one particular work where we show how we can control the propagation of spin waves in the way I was telling you before. We can generate, we can modify how they propagate across an structure by using external ensembles of spins. In the same system, I'm going to show you how we can sense or detect spin waves at the quantum level. This means we can detect the fluctuations even of the quantum ground state of spin waves, which means also we can detect the fluctuations at the single magnon level. And then I'm going to show you conclusions and an outlook of what are we going to do to fulfill the rest of the points of the list. Okay, so let's go a bit more into the physics. Let me just, in a nutshell, tell you how we describe spin waves. Again, spin waves are magnetization waves. It's just a time and position dependent magnetization field. That obeys this equation. It is a phenomenological equation called Landau-Lifshitz equation. Okay, it tells you that the magnetization, the time derivative of the magnetization is proportional to the magnetization times something. And this something is a magnetic field, usually. In particular, you have H here, which is the true magnetic field appearing in Maxwell equations. And then you have an extra term here, which is the term that makes everything interesting or complicated, so, depending on how you want to look at it. In particular, this is called the effective field. And this effective field captures basically all the complexity, all the microscopic complexity that gives rise to magnetic ordering. Okay, this is purely quantum in origin, or parts of it are purely quantum in origin, even though this is a classical equation, and this includes, I put here the symbol of sweeping everything under the carpet, because it's basically what this field includes. This includes magnetocrystalline anisotropy, exchange interaction, dipole-dipole interaction, and many others. But the important thing is that this magnetic field here is also dependent on the magnetization, which makes this equation very nonlinear. Okay, nonlinear. Okay, I want to also mention that this looks like a very exotic field, but basically this is just an electromagnetic wave. Okay, so a spin wave you can also see as an electromagnetic wave propagating in a magnetically ordered material. And the reason is, of course, you have a magnetic field, a magnetization field that depends on time. This will generate a magnetic field that depends on time, and this will generate an electric field that depends on time. So basically, it's just the same kind of excitation as an electromagnetic wave. It only has an extra degree of freedom, which is this magnetization field. Okay, so how do we go about solving this equation? Of course, you can solve them numerically, and this is what we do sometimes. But to be able to do something theoretically, what you first do is you linearize them. And this basically this is similar to the Hosting-Primakov approximation in case, or transformation, in case you are familiar with this. But the idea is the following. So we know there's going to be some external field that is, we assume, strong enough so that all the spins are going to be mostly pointing along one direction. And therefore, this allows us to expand the magnetization as a constant term, which describes this permanent magnetization plus a very small perturbation. And by assuming this perturbation is small and plugging this into this equation, we can neglect terms of second order in small m and have a linear equation. Once we have a linear equation, then we just have a linear differential equation, which we can go to Fourier space and diagonalize. And using some boundary conditions that I won't get into, you can basically find eigenmodes, which are what we can call spin waves or spin wave eigenmodes, and whose mode index I label by just a generic mode index beta. And then the last step is just to quantize them. Okay, you change the dynamical variables, you promote them to Schrodinger picture operators. In a particular way, this requires some careful steps, but again, it is known how to do. And then the final step is, of course, you have to add the losses. Okay, it's not enough to describe them with a coherent Hamiltonian. We know these excitations are very lossy, so you have to describe them with a master equation. So in the end, you have a very, very simple master equation for the density images of the spin waves. You have a diagonal Hamiltonian in terms of these S operators, which are bosons now because they are excitations on top of an equilibrium magnetization, so they are bosons. And then you have, in general, a thermal dissipation. Yeah, just put some references here in case you're interested to look more, where we do basically all these steps are done in detail in our previous work and also by other authors. So, okay, so let me just show you. So this looks quite straightforward, but let me just show you that because of all the weird physics that is encoded in this effective field, what is the phenomenology of these spin waves that emerges from these equations. So let me just show you a very, very simple example, which is a thin film configuration. Again, same figure. So it's an infinite thin film, okay, with a thickness d. And let's find our eigenmodes and let's see what the properties of the spin waves are. So in particular, just like in a dielectrics lab, if on Maxwell equations, if you think, you will have basically two mode indices. One would be a wave vector in the parallel direction, okay, and the other will be a band index, because this is confined in this structure. You will have different bands. And so the first thing we notice is that the bands are very, very anisotropic. Okay, this is something you will never find with a photonic structure this simple. In particular, I brought here frequency as a function of wave vector. For the fundamental band, you can see that depending on whether the wave propagates parallel to the field or perpendicular to the field, you have a completely different phenomenology. Moreover, different bands have very different shapes, and these shapes include really non-trivial points to have in non-trivial features to find, for instance, for photonic structures, such as degeneracy. For this frequency, there are two wave vectors here that have the same frequency. You have minima, and so on. Even more, if you get to higher bands, this is exactly the same structure, but just a higher order band. You find that these bands are completely different shape. So they have completely different propagation properties. And something that is really, really, in my opinion, cool, and one of the most important properties is that these bands and other dynamical parameters can be really tunable by external field and by the geometry. In particular, if I change the value of the magnetic field, I can move my bands up and down. Okay, and you can see I can move them up and down by really a lot. Okay, in this case, by moving by 20 millitesla, I change by 50% the frequency. Okay, this is extremely difficult to achieve with photonics. Okay, to have an external knob that you can use to just move up and down this perturbation so far. And I'm not going to get into this, but I just going to throw a very interesting idea for you that is. What we are one of the things we were looking for in the future, maybe if one manages to integrate these magnons or these magnetic structures into microwave structures, because we have now properties that are unknown for photons. For instance, there is no photonic structure that can do this. Maybe this will lead to us to find and explore protocols that are more efficient. For instance, for quantum state transfer, for quantum information processing, that harness precisely these exclusively magnonic properties, and that they have not been explored precisely because photons cannot have these kind of properties. Anyway, this was just to illustrate for you the complexity of spin waves. Now let me get a bit more into the details and how, and recent work on how we can control the propagation of spin waves using spin ensembles. And so the idea is, again, inspired by photonics and by light, and is based on the following observation. It is known that if you have light propagating in a structure, you can modify the propagation significantly by just placing close to a nanostructure a large ensemble of electric dipole emitters. Okay, and two examples of what you can do with electric dipole emitters are, for instance, the phenomenon of slow light, which you might have heard of, where you basically reduce the group velocity of light theoretically even to 0, or backward light, which is a bit more kind of outsider kind of phenomenon that is not that interesting for some people, in which basically light propagates propagates to one direction, but so the group velocity goes in one direction and the wave vector in the other. There's a lot of studies about how this violates or does not violate causality. But anyway, I don't want to get into that. What I want to get into is that we can import this idea to spin waves, and to be ordered to be able to control the propagation. Okay, and the idea is, if this is a magnetization wave, instead of using electric dipole emitters, we use magnetic dipole emitters. Okay. And so the example, the spins or the emitters that we choose are nitrogen vacancy centers, which you might have heard about. They're basically what you get by removing 2 carbon atoms from a diamond lattice and substituting one by a nitrogen. Okay, these are very good, very known emitters or spin qubits in quantum optics. We choose them for 3 main reasons. The first one is they can be initialized via optical pumping. Okay, I'm gonna be a bit more precise of what this means, but just in a sentence, this means that I can shine a laser on them and I can drive them into their quantum ground state, so that I can have this optical control. The second is that the ground state of the ground state manifold of the MV centers have magnetic dipole transitions, which will couple to our magnetic excitation. So this is good. And the third one, and most important, is that these spins and nitrogen vacancy centers have already been used for spin wave detection. Okay, and this is an example of an experiment by the group of Tuno van der Sar in TU Delft, which is actually our collaborator in this work, where basically they launch spin waves in a film below a diamond crystal, which contains a lot of these MV centers. And then by measuring the state of these MV centers, which you can do optically, you can basically image the spin wave that propagates below the film. Okay, so these are very good emitters for us. So let's see how to describe it. We describe them theoretically. Okay, I'm just going to go through the master equation that describes exclusively the MV centers. They are a 3-level system. Okay, the ground state manifold is a 3-level system and is described by this master equation. The Hamiltonian in particular contains what is called as a zero field splitting. This defines the ground and the excited states of this 3-level system. Then you have an extra contribution, which is a Zeeman field. So if you have a magnetic field, you can basically tune the transition frequency between the ground and the excited state. Then you have dissipators. One accounts for the decay of excitations between the excited and the ground state. The second accounts for the phasing. And the third one, which I'm not going to write because it's a bit involved, accounts for the optical pumping. Okay, and just to tell you what the optical pumping is exactly, I have this level diagram here. Okay, you don't have to look at it to understand everything, but the idea is the following. So we have these 3 levels here. Okay, this 0 and this plus minus. These are the 3 levels that are described by the spin 1 Hamiltonian here. Okay. Now. Okay, now these excitations, it turns out this level structure is at a gigahertz frequency. This separation is a frequency of gigahertz, so it's basically can be resonant with spin waves. And what makes nitrogen vacancy centers so special is that you can apply an optical field, in particular a green laser, to promote all the excitations to these upper optical levels. These are farther tuned. And then because of the weird balance between all these decay rates, if you keep your pumping on, basically it will happen that this cycle ends with all the population being in the ground state. Okay, and this is very useful because if you are at room temperature and this separation is gigahertz, these 2 levels are going to be equally populated, which means that the transition is going to be inactive for the MV centers. So in order for the MV centers to modify the spin waves, which is what we want, you have to be able to initialize them in the ground state at room temperature, which you can do with this optical pumping. Okay, so again, we have these spin waves whose master equation I showed you before. We have these MV centers whose master equation I show here. The only thing that's missing is the coupling, and the coupling is just magnetic dipole interaction. Okay, so each MV center has a magnetic dipole moment, and this couples to the magnetic field generated by the spin wave at the position of the MV center. If you plug the expressions for all these operators, which you can derive and do some rotative approximations, you end up having an interaction potential that looks like this. So this is basically a James-Cummings interaction. Okay, you can the minus here you should understand as the excited state of the MV centers. You can raise, excite the qubit by destroying a magnon and vice versa. And then you have an effective dephasing term that I put here just for convenience or to show it to you, but it's not going to matter for what I'm going to show. So now we have the master equation of one spin, the coupling of one spin to the magnons, and then you basically extend to n spins by summing over all the spin ensemble. I want to mention this again, not super important, but it has to be mentioned that we assume all the spin, all these NV centers to be completely independent. They don't interact with each other, and they are randomly positioned. Okay, good. So what do we do to say how we can modify the flow of spin waves with NV centers? So what we do is basically we trace out the ensemble of NV centers. We are open quantum system techniques, and we obtain a Born-Markov master equation for the spin waves. Okay, and this master equation looks like this. So if you remember, this is exactly again the equation for the spin waves under the influence of the NV center ensemble, and it has the same form as before: a diagonal part and a dissipator. The only thing that changes is that now we have a frequency shift that depends on which spin wave you're looking at, and an increase of the line width for every spin wave mode. Again, I don't want to get into details, but you can calculate both these shifts analytically, and in particular, if you look at the increase in the line width, it turns out to be proportional to three very important factors. The first one is the line width of this of the NV center resonance. Okay, so this NV center, this NV center is a two-level system and has the coherence rate, and the coherence rate appears here. It appears in the form of this Lorentzian resonance condition. This Lorentzian resonance condition is basically telling you that only the spin waves whose frequency is close to the two-level transition are going to be strongly affected by the NV centers, as expected. And the frequency window of spin waves that are going to be affected by NV centers is basically given by the line width of these NV centers. They're also proportional to this rho, which is the spin density, in particular the density of NV centers, which one can control in fabrication. And something that is very important is that they are proportional to the occupation or the population difference in this two-level system. What is interesting about these three factors is that all three of them are in principle tunable, either via external field, which modifies which frequency, which spin wave you modify, or via optical pumping, which basically changes the value of this occupation, as I told you before, by basically 0 when there is no optical pumping and both levels are equally occupied, to 1 when we apply optical pumping. So this basically can allow us to modify just by turning a laser on and off, allow us to modify this rate by 4 orders of magnitude. Okay, so let me show you some results. How do we modify exactly propagation properties? So this is again, so we choose a particular density of NV centers that I'm putting here just to give you the number. But now let's look at the dispersion relation. Okay, this is the same dispersion relation I showed you before for the magnons in a thin film. And what I'm going to do is going to zoom in a very narrow frequency range, which is basically the spin waves that are close to resonance with the transition of the two-level systems. And so this is what I show in these very boring plots. They're going to change in a second. So what I'm showing here is first frequency as a function of wave vector. This is basically a zoom in into the dispersion relation. Then I'm plotting the group velocity. This is the derivative of this curve and tells you how fast the spin waves propagate. And then I'm plotting here the propagation length. Okay, this takes into account not only the dispersion relation, but also the losses, and tells you how far the spin wave propagates before its amplitude decays by a factor of 1 over the number E. And so, okay, so this is again what happens if you have no NV centers or if you are not turning off your laser to initialize them. But what happens when you turn on your laser? It happens that everything changes a lot. In particular, the dispersion relation acquires this kind of S-shape modification, which if you look at the absolute value from 2.6 to 2.7 is not a lot. But the slope of this curve changes drastically, okay? And what this means is that, for instance, in this particular point, when you compute the derivative, you have an increase of 3 orders of magnitude in the propagation velocity of spin waves. Here in this dash region, corresponds to, so here I'm coding the sign. So solid means positive, dash means negative. So here we have a region where the wave vector of the spin wave is positive, but the group velocity is negative, which means we have this backward wave regime. And also we have these points here where negative becomes positive, so we have extremely zero group velocity. So we have the analog of completely stopping light, but in this case we're completely stopping spin waves by using the MV centers. And in particular, you can also see that so this is all maybe not so important for us, but for people interested in using these spin waves to encode information, the true important thing is not how fast they go, but how far they go. And in particular, we see that we also can increase the propagation length by a factor of 3. So, okay, what I want you to get from all of this, to keep in mind, is that first, the spin wave propagation can be modified in multiple ways. Okay, just by turning on my laser, I can either increase the velocity, I can stop them, or I can or can completely suppress the propagation. And I also want you to know, I'm not showing it here, but you can check it in our work, that this modification is extremely tunable. Okay, first, it is frequency selective, which means I can move this region to the right or to the left. I can choose which spin waves I modify. And second, I can just turn it on and off. I just turn off my laser and all the spin waves go to the normal state. Okay, let me just in one slide tell you something else we did with this platform, which is about sensing spin waves. And in this case, what we're doing is exactly the opposite. Okay, instead of seeing what is the impact of all these MV centers on the spin waves, we check what is the impact of all the spin waves on the MV centers. Okay, so we basically now trace out the MV centers, and what we find is basically that we have a modification of the decay timescales, but we also have a frequency shift, and this frequency shift has an analytical expression that is not that important. What is important is that it depends on the position of this MV center. Okay, in particular, it depends on the height of the MV center with respect to the film. Now, this means that by measuring this frequency shift, if you are able to measure the transition of the transition frequency of the two-level systems, you will be able to detect, to infer some information about the magnons. In particular, you will because you will be able to determine the magnon occupation. So this can be done optically, as we propose in the paper, but something that I find more intriguing is that you can do it mechanically. Okay, and in particular, this happens so. Okay, let me just tell you about the optical measurement of frequency shift. I'm showing you here the frequency shift that an MV center experiences as a function of its distance from the field. This is the orange line, and I'm multiplying this by or dividing this by its line width. Okay, which is also modified because of the presence of the magnons. So if this ratio is larger than 1, this means that the magnons are inducing a shift that is larger than the line width, so that you can measure it. Okay, and so this means that for all this range of distances, you can basically be able to detect the presence of the magnons in the ground state. This is at 0 temperature. But what is more interesting is that because you have a frequency shift that depends on the position, you have a two-level transition energy that depends on the position, and this is going to give you a force, okay? And this is what I'm showing here. I'm showing the force as a function of distance. And what is very cool about this force is that even close to 10 to the minus 21, especially if you put, this is for a single MV, but if you put a couple of MVs, you can get easily to 10 to the minus 18. These are forces that can be measured mechanically, but for instance, by taking a nitrogen vacancy a diamond and put it in, attach it to a cantilever. This has been demonstrated with force sensitivities below 10 to the minus 19 and 10 to the minus 20. So in summary, what we are proposing also in this work, and I cannot get into more details because of lack of time, but I will be happy to discuss, is that by measuring either mechanically or optically the frequency shift that these spins, these nitrogen vacancy centers experience, you can basically detect the fluctuations of the magnons down to the quantum ground state. So in principle, this would allow you to distinguish between a single magnon state and basically the ground state. Nobody has done this experimentally yet, but also nobody has proposed yet a sensing mechanism that is so sensitive. Okay, so let me conclude again to make you a summary. So what I really want you to take home or to just to consider is that the magnonic nanodevices, if brought to the quantum regime, could be really great complements to microwave quantum platforms. But that in order to transform this could be into an R, we need to really bridge the gap between the classical magnonics and quantum optics. Okay, I just told you my approach or our approach, which is basically based on this 5-point plan that I just showed you before. I showed you that point one of the plan, coherent generation. I just mentioned it, but we are pretty confident that this is solved. We know how to classically how to generate classical coherent spin wave states. In terms of coherent control, I showed you a way of coherent control. So using nitrogen vacancy centers, you can coherently control spin waves. However, there's I put here in progress because there's also a lot of stuff which we still have not explored and that we are exploring at the moment. One is controlled via acoustic phonons. Spin waves also coupled to phonons significantly. Another is controlled via microwave elements. So you couple a microwave resonator, a microwave waveguide, or ideally a qubit. And the other is further control with spin ensembles. Okay, so this is the kind of my vision for the future. What I have shown you is all that you can do by having a diamond with completely randomly oriented MV centers where all of them are either in the ground state or all of them are not. But because I can control this state spatially, because I can tune especially the intensity of my driving laser, I can in principle imprint in this diamond a magnetic response that depends on position. Okay, this is something we want to explore. We can in principle draw on top of this MV center a response for a magnonic crystal, for metamaterial, and so on. Again, for modeling quantum detection, I showed you a method that we proposed to model quantum detection. So this is in principle possible from the theory point of view, but still, this is not what an experimentalist really likes to hear. They would like to know, or we would like to know, if instead of using this kind of new, completely new method to detect quantum fluctuations, you can detect quantum magnon states with currently used methods. Okay, one is to use superconducting qubits, and the other is to use optical sensing, which is very similar to optomechanical sensing, if you're familiar with it. And in particular, this optical sensing should allow you, if the rates allow, to measure even beyond the standard quantum limit. So this is what we are going to explore. As for generating quantum features, this is still not explored. This is what we are going to do now in the future. And I want to just mention a bit more importantly about the proposing quantum experiments, which is very, very important for us. This is again coming soon, but this is the final goal, okay? And the final goal for us, like, just to reiterate, is not to just do this theory per se, it's just to propose experiments to generate and detect quantum behavior in a magnonic nanostructure. And for this, we envision to, as I told you before, devise ways of generating quantum features, for instance, by performing a local nonlinear operation or a projective measurement, but also to protect them from the coherence. There's going to be a lot of work to engineer band gaps or engineer the nanostructure or the quantum state to protect a quantum magnonic state from the coherence. And also, again, to enhance the current detection schemes, because I don't think anybody expects that with just current optical detection, for instance, you are going to be able to detect a quantum state. You will need to give the extra help. And our goal is to do this, not to do this in 5 years, but to propose experiments that can be done in 5 years. And for this, we are in contact with, we are just actively collaborating with several experimentalists. In particular, my main collaborator is Professor Andrei Chumak in Vienna, who already has a cryostat in which there is already a magnonic waveguide. There's ways of excitations and ways of detection. So together we are working on this, and we are very happy and very, very confident that we can really demonstrate this quantum magnonic behavior in the next 5 years. And so with this, I'm just going to mention all my collaborators. I could never have done this all alone. All the work I've shown was done by all these collaborators. These are the 2 papers I've talked to you about, mostly the first one. And with this, I would like to thank you for your attention. And I'd be happy to answer any questions.
Okay, thanks, Carlos, for this really interesting talk. Is there anyone in the audience that would like to ask the first question? Okay, maybe feel free either to turn on your microphone or ask it in the chat. Okay, so maybe I can start. And I would like you to ask you, I mean, when you were introducing the physics of spin waves and you were talking about this effective field in the phenomenological lambda operation, I mean, I was wondering, since there is this term, okay, so I will wait till you get it. Okay, since there are these a lot of things that you put under the carpet, these data interactions and so on, I mean, I was just wondering if there is any work or study that somehow studies the implications of these unknown or effects that are not taken into account into maybe dephasing or decoherence of your magnons?
No, but it's a great question. This is one of the things I really want to do in the next year. I want to. So there are expressions for this effective field that are all kind of phenomenological or microscopic. What I want to do is to start with a microscopic Hamiltonian that includes all these interactions, trace out all the degrees of freedom that are not magnons, and derive a master equation for magnons that in the classical limit recovers this equation. Okay, and in this way, I expect that I will really be able to model the dissipation, including dephasing, very well. But right now, it is not clear, and that is one of the major things. We know the decay, because this is the same as classical magnetization, but we don't know that whether if we take it to the quantum regime, we are going to have new decoherence mechanisms that are not observed in the classical regime, and that's a key point of modeling the coherence.
Perfect. Thank you. Okay. Anyone in the audience? Okay, we have a question in the chat. Okay, so okay, I will read it out loud. Alberto is asking that okay, you mentioned that spin waves can display strong nonlinearities. How do you make them interact, and what consequences can be expected from this?
I assume you mean how do I make spin waves interact with each other? This comes just naturally from the fact that they are spins. So if you have a spin, you can think of a single spin or a macro spin, and it is very close to, let's say, the bottom of the Bloch sphere, then small fluctuations can be described as harmonic oscillators. But as you go a bit higher in amplitude, so basically, for instance, if you drive them with a microwave, this kind of magnet, you drive with a microwave strongly enough, you will get the spins to start precessing with an amplitude that is larger than what can be approximated by a harmonic oscillator, and you will start seeing the angular momentum kind of commutation relations, and they will see this will come intrinsically as a nonlinearity. And that's actually what people do. They just drive them strongly. What I envision, actually, I didn't talk about this, but there is this possibility of using the fact that spin waves have I don't want to say nonlinear, they have curved dispersion relations, okay, which means that the group velocity is different for different k components. You can use this, and we show this in this paper I showed briefly about generation, that you can use this to start initialize the spin waves in a Gaussian pulse and have this pulse self-compress as it propagates. Instead of getting wider and wider, as usually happens, if you tune the phases right, it will self-compress. And by self-compressing, it will become a spot at which the amplitude is much larger, and then you will kick in a nonlinear response. And that's how that's one of the situations where I think is more promising to elicit a very controlled nonlinear interaction. For instance, you can either, for instance, shine two pulses opposite to each other and have them overlap at a particular point at which they go beyond the nonlinearity threshold and have some nonlinear scattering. But in principle, what you need to do in general is to get the magnetization to be large enough, this oscillation amplitude to be large enough. But there's also, let me just mention, in the classical regime, there's a lot of studies about nonlinearity, like the spin wave solitons and something else called spin wave bullets, and there's a lot of studies about how can we harness nonlinearity.
Yeah, I have a bit of a basic question. I got a little bit lost on the more technical part when you were describing all these master equations of the MV center and the spin wave and everything. And if you could comment a bit, maybe more intuitively, about this frequency shift and the decay. Yeah, I think it's next slide.
This one?
Yeah. So that is the emitter emitting a spin wave, or
no? That is yeah. I went a bit fast. That is so. What I'm doing here is just kind of, I'm tracing out the degrees of freedom of the spins in order to obtain a reduced density matrix, in the same way as I can take a two-level system in the presence of an electromagnetic field in free space, trace out the electromagnetic field, and get a master equation that includes the decay of the spin waves. Of the two-level system. In this way, I do the same. Instead of having the free electromagnetic field, my bath is the ensemble of spins. I trace it out and I get an effective equation. And in this particular effective equation, because of particularly simple configuration, I just get that the spins, well, as always, you get that the spins, that the path modifies both the coherent dynamics and the incoherent dynamics. In particular, it gets you a frequency shift, which is analogous to the lamp shift, but in this case, by a spin ensemble, and it gets you an extra contribution to the decay rate, which, by the way, in the case of spins, can even be negative. Okay, if you get population inversion, you will get just pumping of excitations into the system, and you will get basically negative decay rate. So the reason why this happens, in particular for the gamma, is relatively easy. You basically you put your spin waves in contact with another bath, so spin waves probability can get into the bath and be lost, and that's why you have a different kind of loss channel. And well, this comes accompanied by a resonant behavior. So basically, your bath is kind of has a resonance, and this has an energy structure that is not flat. It's a Lorentzian because it's a two-level system, and this generates that the spin waves will. If you want this delta, you can imagine as spin wave scattering against all the NV centers. Okay. And this scattering results in a constructive or a destructive interference that makes spin waves, makes it for spin waves easier or more difficult to propagate at a given wave vector. And this moves a bit their energy. This is how you can interpret it. Does this answer a bit your question?
Yes, yes. It is quite analogous to the electromagnetic case, right?
Exactly. The procedure mathematically is exactly the same, which you can apply to any kind of math. That's the cool thing. Yeah.
Yeah, great.
Okay, so anyone else has any question for Carlos? Okay, so if this is not the case, okay, we can finish here. Thank you a lot, Carlos. It was a super interesting talk. And thank you all for attending to this seminar. And we will get in touch with you to inform you about the next seminar. And Carlos, we will send you a certificate.
Thank you. And if anybody wants to know more, I'd be happy to answer emails. So feel free to write me an email. It's okay.
Perfect.
Great. Thank you very much.
So thank you and see you all. Bye.